Good. So I think we can probably start. Thanks everyone for joining on this new edition of the Cambridge ELLIS Unit seminar series. We are really excited to have together with us Cheng Zhang. Before presenting her, I would like to thank the sponsors of the Cambridge ELLIS Unit, Invenia Labs, Microsoft Research Cambridge, AstraZeneca, Cambridge Innovation Capital, IQ Capital, Second Mind, and Schlumberger. Today's talk is by Cheng Zhang. She's going to talk about deep end-to-end causal inference. We know Cheng very well. She's based at Microsoft Research Cambridge, here in Cambridge as well. She's a principal researcher at Microsoft, and she leads the project AZUA, which focuses on efficient decision making. Before joining Microsoft, Cheng was a postdoc at Disney Research in Pittsburgh within Carnegie Mellon University, and she received her PhD from the Department of Robotics, Perception and Learning at CATE Royal Institute of Technology in Sweden. Her general research interests are in causal machine learning, deep generative models, and approximate inference. And it seems that what she's going to talk today about is related to all these things. Yeah, so I will stop sharing my slides, and Cheng, I think you can share your presentation now.
Yes, let me share the screen. Thank you very much for the introduction. Can everyone see the slides now?
Yeah.
Great.
Good.
Then I'll start. Thank you very much for inviting me to give a talk here. And I'm very happy to see there are so many people interested in this type of research. So before I start, I just want to thank all the collaborators. So this work today, it's the effort of the big team, and especially Javier Antoren, Thomas Gaffner, and Adam Foster, who put a great effort on making this work. And I guess it's CBL. You also recognize many familiar faces, Chao, Ma, and Ben Bogon are alumni from CBL, who's currently in Microsoft Research, and Javier is still in CBL. So I know they're all in the audience, so if you have really difficult questions, feel free to challenge them anytime. So I'll start. And so people care about optimized decisions. For example, as shop owners, they may think about, okay, should I do buy 2 for 3 or 30% discount? Which one will give me better revenue? And maybe a medical doctor, they will think about, okay, now I have this patient, should I give treatment A or treatment B? Which one will be better for this patient? So this decision making is everywhere all the time, and we want to optimize the decisions. And if we want to use machine learning to optimize the decisions, this will actually be causal questions. So just to give some examples, why it's causal questions. Let's say among all the shops, I want to decide the program, whether I want to buy 2 for 3 or 30% discount after the Christmas. So what we can formulate is as we can figure out the average treatment effect. So the average treatment effect is defined here in this example. So we can think about our target is the revenue. So this is X, Y. And what we want to know is, for example, compared to given no discount, this is reference. What if I start to launch this buy 2 for 3 programs, and then I want to compare the expected revenue of this buy 2 for 3 compared to expected revenue if there's no discount. So this is the average treatment effect. Then, of course, if we want to see what about another program, the 30% discount, and then we can compute the average treatment effect for this 30% discount. And then the decision making is easy, because if the first program buy 3 for 2 is have a higher ATE because they will just drive the revenue higher. Clearly, that's a better decision, right? So be able to compute average treatment effect. This is one of the typical causal quantities that can help us to make the decisions how to choose these programs. And another type of causal question that can be, let's say, if this shop owner owns many shops around the whole world, let's say, how to choose this program in UK and how to choose this program, for example, in Fiji. People may be reacted to this very differently, right? Because I think Fiji is much a tourist-driven country and the population have a very different culture, right? So then we can compute something called conditional average treatment effect. It's very similar to the average treatment effect I defined. So we still have this different program, but instead now we have conditional on the country. So we can conditional on if the country is UK, and we can also conditional on if this country is Fiji. So we can do the same thing. If we can compute the conditional average treatment effect, we can make a decision, give what we condition on, like a different country in this case, but in healthcare case, it can be conditioned on different age group, etc. Like all condition on this person's socioeconomic situation. So hopefully I convince you that the causal questions are very important, and then we need to answer this question to optimize our decisions. And let's recap it. So for commonly, what is the goal is we commonly have historical data because A/B testing is commonly not available. It's not ethical to causally. So what we can do is commonly only have historical data. This can be, effect, treatment effect, like different medicines, revenue, etc. But it can also be, for example, like a medical treatment, health measures, and all these things. And each row is just a data point. And we commonly want to specify our causal question. What is treatment? What is effect? And sometimes what to condition on. And then what we actually want to get is these causal quantities. It can be average treatment effect, conditional treatment effect, even individual treatment effect. And with this quantity, we can make decision. So this is the decision-making process. Here is input and here is output. So commonly, these are really hard. Like supervised machine learning cannot do it because you will never be able to give the same item that is 30% discount and no discount. So we will never have the truth for a same item. And so a field is called causal inference is needed. Then we can have some method kind of answer these questions. However, the existing causal inference method is really not sufficient to answer that. And why is that? Because commonly, they require additional input, looks like that. They need to make assumptions about the causal structure. So sometimes they need the full graph. Maybe even they don't need the full graph, they may ask you, okay, what's the confounder? What's the instrument variables? So they require additional input that asks the domain person to tell you kind of the causal relationship between the variables in different degree. And in most of the cases, they are not available because in real world data in healthcare, there's like 100 variables for every small single thing like a person do. And then in business decision making, it's the same. Like in Microsoft, we may even have hundreds of engagement programs with different partners. So have the full causal knowledge from the domain, it's just impossible because they actually don't know about it. Even they know, sometimes it's maybe very, very incomplete. So this is the typical causal inference method. So commonly, they require two steps. One is causal identification, one is causal estimation. So identification is, I think, people know about like a backdoor criteria and all these things. And sometimes they choose what's the instrumental variables. So these need a certain degree of the graph knowledge. And then after this graph knowledge, then you can do the estimation. So there's a traditional method, it's just to compute a simple conditioning, like we do calculus. And then there's more machine learning based, like a double machine learning, and sometimes there's causal forest and all these things. So you can see this causal inference, the whole field, they require this type of domain knowledge as the relationship among variables. And these are very hard. And so we cannot solve our problem because it doesn't exist. How can we do about it? And so then people may ask, okay, why don't we do causal discovery? That's a good, good solution. So what's causal discovery, this field about? This field is all about if we have data Like it can be, it's just a historic data. It can be observational data only. It can also be mixed of observational and interventional data. And the output is a graph. What's the relationship between all these graphs, all these variables? I think that's great. Just as I know, many people in CBL are, I think, more on like Bayesian machine learning. I will give a little bit more introduction about causal discovery method. And so commonly, historically, what are the causal discovery methods available? These are functional causal models, score-based method, and constraint-based method. So how do they work? So for function causal models, so what they do is they assume certain functional form for how like the cause and effect, like the underlying generative process actually work. And one example is called Lingam. Just to give you a flavor, let's say it's a linear non-Gaussian model. By the way, can you see my cursor?
Yes.
Oh, great. So in this case, with this assumption, it's this is a linear model. The noise is non-Gaussian, and you can see this example. So the data distributed in this way. So if you do the regression, assuming that x is the cause, y is the effect, then you can get the noise, the residual epsilon, and x. You can see epsilon and x are independent. But if you assume the other way around, if you assume y is the cause, x is the effect, you do the regression again, and the noise distribution, the residual, and the cause, you can see that they are not independent anymore. So because commonly the noise and cause, this would be independent, so this must be wrong, this is correct. So when you assume certain functional form and certain noise form, you can actually identify which direction is the cause and which direction is the effect. So these are commonly how can we use functional causal models to identify the causal graph. So then the second type is score-based. So the whole big idea about score-based method is which graph describes the data best. So you have the data, you can think about all possible graphs, and you define some objective. Means the basic one can be just a BIC. So you compute all the scores, and the one describe the data best is the result. So commonly, as a functional causal model, already need to assume different function form because in certain cases it's just not identifiable as this is Gaussian. For score-based method, so you also have the case, sometimes you just cannot tell like A cause B or B cause A. So what the output is called Markov equivalent class. It's just a group of these graphs. They're all equally likely to explain this data. And third type is constraint-based. So the constraint-based is based on independence test. So commonly you assume all the variables are connected, and if you start to do independent test, if these are independent, given conditional on some variable, they cannot have a causal link. And after you do all the conditional independence tests, you get a skeleton, and then you have some rules to orient the edge. For example, if you condition on C and B are not independent anymore, but the condition on other variable, they're independent, so it means it must be a collider structure. So not all the edge can be fully oriented, so it's the same for constraint-based method. They also output a Markov equivalent class. I mean, for the basic constraint-based, for example, the PC method. So there are many other constraint-based methods as well, but commonly they output a set graph instead of a single one. Okay, so these are three types of causal discovery method. And I just want to introduce another one that is because of you can think about like for score-based method, you need to search for all possible graphs. And once the number of nodes grows, it's super exponential number of graphs. So it's very scary when it comes to compute. So there is a method proposed like in recent year, which is called DAG with no tiers. They want to convert it into a continuous optimization problem. So what they did, this contribution is instead of thinking about searching the DAG space, they want to propose objective, and then they actually propose a way to characterize what's a DAG, what's a kind of count how many cycles a possible graph can have. So in this way, they can convert it to a continuous optimization problem, So in particular, in that paper, they are thinking about linear model, and then they want to optimize kind of just L2 loss. Of course, this loss can be anything. It can be kind of likelihood-based loss as well. But what they did is that constraint in general, they kind of say the trace of the adjacency matrix should be D if it is a DAG, otherwise it's not. So if they can find this kind of DAG loss, so you can put it as a continuous optimization-based method, so that can help this traditional method to scale. So that's one of the important, I would say, advancement when it comes to scalability of causal discovery method. And this method is both functional causal models and score-based. So it's also to show not all methods need to belong to one class, it can be hybrid class. Okay, so now we have an overview of causal discovery method. So why do I want to have this overview? Is you can see that first, for causal discovery method, not all of them estimating the functional relationship. For score-based and constraint-based, they only give you the graph, and the graph may not be a single graph. And if you only have a graph, you don't answer the causal inference question directly, so the output ends there. And so if you have functional causal models, that may be easier to answer causal inference question, but that's not guaranteed. So there are a lot of assumptions associated with it. So from causal discovery method itself to answer causal inference question, that's not very straightforward. We need to think about how to combine it. And so, okay, now we want to combine it, as the word is very beautiful, but there are still many problems. So first, causal discovery and causal inference, these are actually almost evolved as two separate machine learning directions. People advance them in many ways, but these are rarely being put together as one question looked together. Although in real life application, people actually just want to give you data and answer everything, which requires these two to be looked together in an end-to-end way. So being developed, many work developed separately really does not help the end user to solve their problem in an end-to-end way. And secondly, I'll show you more problem. So because many work has been only either focused on discovery or focused on inference, there can be different assumptions. Because, for example, the many score-based method and many constraint-based method, they output like a CP-DAG, which is a completely partial DAG, means some of the edge they cannot orient. It's a set, it can be possible graph 1, it can be possible graph 2, they share the same independence relationship, but this can be two graphs. And PAC, these are more ancestor graph, that's even a little bit more complicated, and there is a lot of like MAG and every different graph. And sometimes now we have probabilistic method. We output a whole distribution of a graph. That is not even Markov equivalent class, but just, okay, I want to say this graph have probability 0.1, that one have probability 0.3. So it can be a distribution of a graph. So of course, this is useful because only discovering the inside of the graph is already very useful for many applications, but it may not necessarily help the causal inference, because when we answer causal inference question, many methods actually require a DAG. It's just require I only give you one graph, and that need to be the true graph. Then I can use this true graph to identify, okay, what's the back door, what's the front door? Or like in another way, or some other method, what they actually require is find the instrument variables. But in some way, just some knowledge for the full graph, I don't know, but for the part I actually need to know, it need to be fully known. So you can see there's a problem. The output of causal discovery and the input required for causal inference, they may not be in the same form. And it's not very trivial to put them into the same form, because how to manage them, it has been rarely put into research together. So in recent years, there are more and more people realize it, and there are work, for example, where I cited here, that they start to look at how can we do inference consider Markov equivalent class. But these are work, of course, there are a lot of theoretical work put into this type of work, and commonly they may solve one type of question at a time, like a CP-DAG, only CP-DAG. And then this method cannot be generalized to if we have a distribution of DAGs, how do we handle it? So that's another problem. Okay, this problem doesn't stop here. I'll show you another type of problem. These are just examples. Because of these two domains has been developed separately for causal discovery. We always need assumption. So if you don't make any assumption, nothing works. So we always need to make some assumption. So let's say functional causal models. What we show is like we can do lingam. It means the functional form is linear, but the noise form cannot be Gaussian. If it's Gaussian, it doesn't work. Or the functional form is nonlinear, then we can have additive noise model. The noise can be other forms. So this is an example of functional causal models assumption. Of course, there are other assumptions as well. But then let's say another example. For many basic causal inference tools, they actually require linear Gaussian. So the functional form is linear and the noise have to be Gaussian. It doesn't work when the noise is non-Gaussian. So you see the problem. So the assumption of causal discovery and causal inference, they completely conflict with each other. So if we want to just take a causal discovery method and combine with causal inference method, even you can have a DAG, the assumption don't overlap. Even think about you, because these are just two examples. For some other example, maybe it's not that bad. So it overlap, but you are taking the worst from the both world. You are just making the scenario that can be applicable to real world, like narrower and narrower, because you need to combine the assumptions from those domains. So hopefully you can see why there are so many problems if we look at this separately and we want to solve a real world problem. Okay, so now here, what we want to do is we really want to help real world users, to help them to optimize decisions. And that's our goal, right? So what we actually want is we want to have input data, the observation we have. We can let user ask questions, treatment, effect, how they can specify it. But we want the model to do all this together. We want to output the causal graph. We can directly estimate the causal quantities and help user to make decisions. Of course, you need to estimate the functional relationship to estimate the causal quantities. So these are more byproduct output. So we want input data and output the whole thing together, and we look at it together. I think that's the way if we really want to make a real world impact, that's how we need to look at this question. So that's the reason our team, we have been looking at it together, and we developed a framework called Deep End-to-end Causal Inference. So just a little bit more primer. So in causality, we commonly describe the causal system with structural equation models. So it tells you it's like what's the underlying process, like how a particular X is generated depends on its parents and a noise variable epsilon. And then in this work, we're going to work with additive noise model. This is one of our assumptions. So it just means it's a special relationship. So the functional form is not like an arbitrary noise and parents relationship. So it needs to be a function of the parents with a noise that is additive. So you can see it's additive noise model. So each noise variable depends on a function of its parents with a noise term added. And then you can also write in the vector form. So it's the same. So in this work, we're going to work with additive noise model. So this is one of the most common SEM people work on. So in the future, we definitely want to expand it. But for now, we work with additive noise model, and the F can be nonlinear. So recall our goal. We want to have the data. We want to use the data to estimate the causal relationship, functional relationship, and then compute the causal quantity and make a decision. So our objective is we want to learn the causal relationship and functional relationship first. And as Miguel already introduced, my background is Bayesian machine learning. So we'll use a Bayesian score-based method. So this is a high-level objective. It have a history from Bayesian network already. So that what we want to optimize is want to find the graph that maximizes the likelihood. And so this is our objective. We want to model the graph G and then how the data is generated under this graph G. And then it's more come to the specific. How are we going to model the prior and the likelihood term? So here in this work, we're going to use a flow-based method. And so in here, we're going to choose PZ as a Gaussian with learnable variance. And we're going to choose the transformation in this way. So you can, this G is, FG is invertible as far as G is a duck. We show it in the paper. And I mean, we're working with causal model, so we want to enforce G is a duck, so it's invertible function. And then you can see that we just move things around, and you can see this recover, it's like respect the additive noise model form we're working with. So this is a assumption. You can see we can write it as the additive noise model. This recovers the structured equations. And with this, we can have the flow-based likelihood term in this way, just to use the standard transitional variable formula. So our choice of likelihood is not completely new, but it's kind of new. So because there is one related work called causal autoregressive flows. So we kind of have the same idea as the likelihood choices. I just want to point out in this work, in their work, they need to assume the graph is either given, so it's a predefined order, the G is given, or if they do causal discovery, they can only work on two variables, so they generally only have pairs. So in this way, you can view our work as extending this autoregressive flows as be able to automatically learn the graph and be able to extend to arbitrary number of variables. And so now we need to choose our prior. So of course, as we said, we need to work with DAG. So this is also one of the assumptions, so there's no cycles in the graph. So it's directly a cyclic graph. And we'll just kind of utilize the idea from the Notier paper we mentioned before, like the paper converts a problem to continuous optimization. They characterize the DAGness in this term. So if this equals 0, then it means the graph is a DAG. So that's how it inspired our prior. So we set our prior in this form, and this H is the same as a DAG loss here. So we have as a phi and alpha parameter. So during training, we'll increase it so that we encourage it to be a DAG in the end. And this is the general like regularizer. Okay, so in this way, we'll kind of enforce, at least in the end of the training, it is a DAG, and so that it's for sure invertible.
Can I ask one question here? Yeah. So you have this quadratic term. So you have the HE appears in the prior in two ways, with a quadratic term and a linear term. Yeah. Could you say a few words about why these two terms?
So we'll just use the argumented Lagrange to update it, so that to make sure it goes, so this goes to 0. Mm-hmm.
Okay, so it's like a constraint. You will use this. You will use this HG as a constraint, and you include it into your objective with the augmented Lagrangian method, which has these two terms. No, it has the quadratic term and the linear term.
Yes. Mm-hmm.
Okay. And then just another question, quick on this. What would be W0? Yeah.
So here, like it's more like a sparsity in some way. So in general, you want the graph to be sparse.
Mm-hmm.
So it's a sparsity term. Mm-hmm.
So W0 would be like a sparse adjacency matrix for the graph.
So it's an adjacency matrix that to be sparse. You can commonly, I mean, if you can set it to extremely small value, or you can even set it to 0, mm-hmm. Or if you actually have certain sparsity preference, mm-hmm. You can also set to other values.
Good, but I see in the prior you have this Frobenius. I assume the F is the Frobenius norm of yes. These matrices.
Yeah.
Okay, and then what I would expect is that G gets close to W0. No, you want the adjacency matrix of G to be closer to that of W0, and W0 is some pre-specified sparse graph. Is that right? Or
yeah.
Okay.
It's a specified very, very small value in general.
Okay, good.
Okay, cool. Thank you for the question. Hopefully that clarifies. And so then it comes to inference. I mean, so G we can treat it as like a global variable. So it's intractable. And we just take our most standard term, like a inference tool, variational inference. So we have the QG. So in general, we do mean field variational inference. We have the Q5G, and then we constructed the evidence lower bound and optimize it. So this is a fairly standard mean field variational inference. Okay, so now we can optimize the
one more question. Could you say a few words about the form of a Q5? Like what type of distribution it is? It's
So in general, like I think here we have been very brutal about it. So there are two ways. So we can just have the adjacency matrix, but you can also have the adjacency and orientation as a two matrix. Like so we have the adjacency and orientation as two matrix. Like that's how we parameterize the G. And then for each edge, we actually treat it as independent. I mean, that is very brutal to assume each of the edges is independent, but that's how we parameterize. In general, the G, it just tells you how likely the existence of each edge, and these are just Bernoulli.
So G would be binary. I mean, the entries in G are binary. And exactly. You have like some sign for the direction of the edges, or I know it's you wouldn't have that, no? So
it's just all binary because binary shows it exists or not exist, and then another binary shows whether it's forward or backward.
Yeah, good.
I mean, you can use one binary if you use a full matrix, and you can put the adjacent orientation as two matrix. I think this doesn't change this, but it may have a little bit of impact on the optimization.
Good. We have one question in the chat. The question is, are we concluding that we end up with a single DAG within a Markov equivalence class using this setup?
So because we are assuming this is nonlinear additive noise model, so this type of model is identifiable, so you can be able to find a single DAG. And then first you can, and secondly, with our like kind of how we use the DAG loss and annihilate, so we commonly like encourage to convert it to a single DAG, but it not necessarily converts to a single DAG. It can be bimodal.
Good.
Okay, so I think that question also relates to the theoretical considerations. So we actually show that if we have infinity data, we can actually recover that true single DAG. There is some assumption associated with it. I will not go into the detail. And actually, if you have a question about the detail of this theorem, you can ask Wenbo, who's actually in the audience. So this is in general. So with infinite data, we can convert to that single DAG. But of course, realistically, we never have infinite data. So our posterior are not necessarily single mode. Okay, so now hopefully I conclude this part. What I showed you, like the method, what we can do already is with input data, and then we can find the causal relationship because the DAG we can find is up to here, so we can find the causal relationship, and because we are learning the whole function together, so we will actually implicitly have the functional relationship because we are learning all the likelihood, right? So then the parameter of the neural network kind of implicitly tells you the functional relationship between the variables. Okay, so now we can do the first step. How can we do the causal inference? Because we still need to compute the causal quantities to make the decision. So what do we have now, right? So also show with the question. So we have the
sorry, I have another question about the framework. So I find it so you have this functional relationship which is based on the noisy additive model, but you are not really. I mean, in the example that you showed, for example, with these functional methods, typically you identify one direction or the other using some independence tests. But within this framework, you don't have any independence test. Is that right? I mean,
we don't have the independence test. So in some ways, optimization procedure is more similar to a score-based method because what we're doing is just optimize the whole objective. It's not like calling it a functional. It's just because we assume a functional form. It's a nonlinear additive noise model, but we are not doing things like a lingam, like fix the model and doing the independence test. But rather we just optimize in some way the score and get this relationship.
Yeah, Good, that's clear then.
Yeah. And meanwhile, by the P assumption, all the Z are independent, right? Okay, so then we come to the causal inference part. So what we have from what I talked before is the estimated posterior of the graph, right? And so what it looks like, it can be, this is a real example actually generated by Javier, a toy example. What we estimated is the left one, 0.6 chance, that's in the left graph, and then in the right graph is 0.4 chance to be this. This is approximated posterior, right, of the graph. So how can we do causal inference in this case? So as being part-time Bayesian, so we just take a Bayesian lens for causal inference. So instead of dealing with given a graph and compute the ATE, we just say, let's compute the expectation of the 8 and CATE given our distribution of the graph. And so, for example, let's say the average treatment effect, this is our definition before, doing the average effect, the treatment effect given treatment A compared to given this reference treatment B. So how to compute, what does the do operator do here, right? So just very basic, right? So when we do something like do treatment equals A, what happens, what happens in real data generation in some way is you cut the incoming edge for this variable you want to do. So because you want to set this to a particular variable and cut all the incoming edges. So this is what the do operation actually does to a graph. And then in this way, what we can think about, so your probability of other variables, anything here, given do treatment equals B, given the original graph, is actually the probability of this, by cutting the incoming edge, of this being treated variable. So what we call is mutilated graph, because you cut this edge, and then set this variable into its particular value. Okay, I should set it into B. Apologize for that, but you got my idea. It's just to cut the incoming edge and set it to a particular value. So then in this way, we can, because we have everything, so it's a generative model, we can just cut this edge and we'll be able to generate all the examples. So just from a Bayesian lens, what I call it just the magic sauce is Monte Carlo estimation. So we can compute ATE, just can use Monte Carlo estimation of these terms, because now this, how to compute this term is just by sampling. You can, cut this incoming edge of the T, we have the graph, you cut that edge, you can set this treatment variable to the one you want to do, and then you can sample your target variable. So then in this way, you can do Monte Carlo estimation of all this term, and then you can get your estimated treatment effect. So it's very simple. We just take a Bayesian lens to estimate the average treatment effect given a kind of sample of graph. Because when you do this, you always sample your graph from your graph posterior as well and do this procedure.
Can I have one more question? I think it's just a small detail. So obviously you have here different graphs that are sampled from your variational distribution. Yeah. And my question is, what happens with the functional form connecting the different variables given the graph? Because I mean, it's deterministic how this is learned, or it's like it depends on the graph in some way or so. I mean, you haven't really shown what happens with the functions f, and do you learn point estimates for this, or do you integrate them out, or how is this?
So we run, I believe we run point estimate on the parameter for the function f.
Okay, and then it's just okay, so I assume then the graph is just kind of switching on and off variables in this functional form, no?
Yes,
so, yes. Okay.
So I mean, if there was a 1 indicating there was edge, and mutilate the graph just means setting a 0, right?
Yeah. Good.
Okay, and so then this is standard Monte Carlo estimation if we treat the ATE estimation in a Bayesian way. Okay, and so it's very similarly goes to conditional treatment effect, but there is a little bit more problem with conditional treatment effect, because when we want to compute this term, we need to compute it in this way. So the lower part is actually intractable because we need to marginalize out of the xy, right? It's a wrong direction marginalization. And so what we can do is, what we're good at is we can sample, right? So we can set any conditional thing, then we can get treatment and effect. We can sample a lot of them, right? So if we can sample a lot of data for all the variables by setting any condition. So what we can do is we can train a surrogate model. So in general, we just want to train a surrogate model to fit the effect variable and the conditioning under the different treatment. So given one treatment, we can sample all the conditioning and we can sample all the effect, then we can predict, and given any condition, we can predict any effect. Okay, I think the picture is better in this sense. So what we're doing here is like the same example as before. So we have different graphs, right? This is what we learned. And so what we can do is we can, then the upper part is a ground truth. So we can model like the ground truth effect variable and the conditional variable. So this is an observational distribution. These are the ground truths. If you do intervention, how the distribution look like. So these are the intervened and reference means treating it A, treating it B. So what we can do is we can generate a lot of data of the XE and XC. So we can fit the distribution of all the samples of XE and XC, we can estimate it. And then we can do the intervention. And with the intervention, we can generate a lot of this data. Then we can estimate the function of predicting XE from XC. So you can see these are the orange one supposed to be the reference, and the green one can be the treatment. It means like we set this was treatment equals A, like the do A, and this is the do B. And then we can estimate this surrogate function. And so we can do this. This is corresponding to the graph A. This is corresponds to graph B. So we can compute in general with this prediction surrogate model. We can compute the conditional treatment effect given any graph sample, and then we can just marginalize over this graph, so we can get the final CATE estimate. So it's supposed to be conditional average treatment effect. Does it make sense? Okay, I think Javier plotted this.
Maybe just to clarify so that everyone gets this. So what happens now is that you want to estimate these conditional expectations, no? And then you have a model that can generate data, but it cannot really give you these conditional expectations. Is that right? And that's why you need to really sample data, synthetic data from your model, and you learn a surrogate model that estimates the conditional expectations.
Exactly.
Good.
And then you marginalize over graph again, so you got your final CATE estimation. Okay, cool. So this model actually works great. I think this is really solve all the problem, but I want to mention some additional assumptions for the model I described above. So first, I said it's a nonlinear additive noise model, but you see our base distribution PZ was Gaussian. So it means we are doing nonlinear additive noise model with the noise form being a Gaussian noise. And secondly, you can see we have been mainly dealing with continuous variables. So all the proof and all these things, it's only work with continuous variables. And the last is we assume like the data table, everything is observed, there is no missing value. But in real world, this will be really constraining because we want more flexible noise form, because not everything is Gaussian noise. It can be uniform noise. It can be any other noise form. So we extended the model to be able to use spline noise model. So because each of the noise, they are independent, right? So they are just added to the variable. So the idea is fairly simple. You're just doing a spline flow on any of them, just a single dimension. And then we also extended our work to be able to handle mixed type of data and be able to handle missing value. So this relates to a lot of old work we had in our team with deep generative model to handle mixed type of data and handle missing value. So I'll not dive very deep into this. So if people are interested, you can read our paper about it. But I want to mention one more thing, is I presented the DECI framework. That's a deep generative model. I can do end-to-end causal inference. But the whole idea to kind of using a Bayesian lens to treat causal inference can be generalized beyond it. So let's say if we have an example of the CPDAC, so an algorithm like a constraint-based causal discovery may output something like this. Then this output means it can be any of this graph on the right-hand side because they share the same conditional independence relationship. So what we can do is we can simply just treat them having the same probability, and then we can do causal inference based on that. So it's a very easy and simple Bayesian way on doing compute the causal inference quantities. So if we have this way to see this problem, so this framework can be used for any arbitrary causal discovery and causal inference. So the DECI itself, we can treat it as a discovery method by itself and combine with other inference method. Or we can treat it as an inference method and combine with other discovery method, and we can let other method combine. So we can use it end-to-end as I presented. But if you really are a fan of double machine learning or something like that, you can also use DECI for causal discovery and then use the discovered graph as input for causal inference, like let's say double machine learning, for example. You can use other things as well. And you can also use, for example, PC, which is a traditional constraint-based causal discovery method for discovery. Then you use DECI as the inference method. And so in this way, what we can do is even better, because for DECI, we can use PC output as even a prior. So we can actually, instead of building the prior as a sparse prior W0, which just tells everything should be sparse, we can use as a discovery method as our prior and do the inference part. And we can also use PC as discovery, double machine learning as inference. So you can do any combination in this way. Okay, so then I'll just use the last couple minutes to show some brief results. So this is results for causal discovery. So we will show you results in different evaluation. So these are different synthetic data. So in general, the first number is number of nodes, the second number is the number of edges in the graph we generate. We have a lot more in the paper. And these two are two kind of semi-real data set. So this kind of, you still generate data, but this data have meanings, and they were having associated with a lot of real world functions to generate it. These are two standard causal discovery benchmark. So we look at adjacency, orientation, and causal accuracy. So the higher is better. So what do we want to show here? So the gray and the red, each column is a data set. We just link them for visual for you to be able to find the dots. So the DECI S means with the spline noise model, because some of the noise are not Gaussian. So you can see the gray one compare with this blue triangle one. The gray one is better because when the noise form is more flexible, it's in general give better performance. And you can see it's in general better than a lot of other baseline. We can have no tier PC, no tier SOP, Lingam, Grandag. So we have a lot of other baselines. So in general, our method perform very strong. And secondly, you can see the PO, the red one, compared with the gray one. PO means partial observation. So we drop 30% of the data completely at random. So you can see with a little bit less data, partial observation, the method still works quite well. Of course, it works slightly worse than the full observation because the data volume is a bit less. You can see it still kind of work very similarly. So you can see we can handle partial observation very effectively. And the results in general compare with other like a standard baselines on discovery is fairly good. And then we also show you this is average treatment effect estimation. So we created a lot of this. We call it a causal suite data set, more synthetic data with different relationship. I'm just showing some example here. And so as, for example, here is linear Gaussian case, and here means linear exponential noise. So Gaussian noise, exponential noise, both are linear, and this is nonlinear. These are just two nodes. So we can see that with linear exponential, so when the noise is non-Gaussian, this is Gaussian, this dark one is the spline noise, you can see it perform significantly better than the ones assume the noise is Gaussian. Because that's the correct assumption, but when the noise is Gaussian, the difference is not that big. And the bottom one, this one's T means true graph. We just give a reference. So what if the true graph is available? So of course, true graph is available is always better, but depends on how good is the discovery quality. And linear and nonlinear, these are linear, like dual linear and dual nonlinear. Dual linear is just a linear causal inference method, and dual nonlinear is actually double machine learning method. So this can be very competitive as well. One, it is, you can see the yellow one. So it can be very competitive. One is properly estimated, one the graph is correct. But in general, the DECI spline is the one like without true graph, you can see have the best performance. And we also evaluated on like causal inference benchmarks, twins and HDP. These are also this semi-real world data set. So these are real world data set, but with human induced kind of sampling method on top of it. So in general, you can also see the end-to-end DECI with spline noise have the best performance. So in our paper, we actually have more than 1,000 experiments with a lot of this synthetic data, with random generated graph, with benchmarks, and with like a Simpson and all these different special cases. So here is a rank. This is over 800 experiments, and there is another 600 experiments for the discovery part. So these are over 800 experiments. You can in general say without true graph, so the DECI spline perform like best in general. And also if it's a DECI spline, when you have a really good discovery method, if you combine it with double machine learning, it's also a nonlinear inference method. So these two actually can be very similar. I mean, it's expected because double machine learning is a very good estimator. These perform top, and DECI Gaussian also perform fairly good because the data set, many of these data sets have no Gaussian noise, some don't. So in the final rank, one is the Gaussian noise. In this case, the DECI Gaussian can perform very good. And once the true graph is available, I think other method, just to treat it as a pure inference method, it is still very competitive. And now I want to show you a little bit more CATE example, because for conditional causal graph, we're not going to do two nodes only. So these are the two examples. One is, we call it the sim product Simpson. It just means the relationship between the parents. These are product relationships, so it's not, the relationship are not very simple. And then this means large backdoor, because for this case, if you do backdoor, you can do control on any of these nodes. So you can have a large set of the backdoor choices. Okay, so here are the CATE experiment on these two synthetic data and the two benchmark. I think the results is fairly consistent. I mean, it's a deep learning based method. Sometimes we have this very different performance. Clearly, I think for some random seeds, it may not necessarily always converge, but you can see in general, the DECI spline end-to-end delivers like a very competitive performance, even for like a CATE estimation. So I think the time is up. We have 2 more minutes. So here is a summary. So what I introduced today is end-to-end causal inference. So I really want to, from a real world impact perspective, to look at the problem from discovery to inference in the end-to-end way to solve the real world problem. And I presented our specific method. It's called DECI, a deep learning based method, where we provide theoretical analysis, we have real world data consideration to handle missing value, etc. So this is in general a very competitive framework. And we also talked about this type of using a Bayesian lens for causal inference can be generalized as well. So the paper link is here. We're going to release our code very soon under our Project Azure repo, hopefully very soon. And thank you very much.
Good. Thanks, Cheng. I think we can have a few questions from the audience. If anyone wants to ask any question, please just write it on the chat. I think we have already some there actually. Let me see.
There is Shirley. Leo said, could you repeat this part? But sorry, I just see it. So can you tell which part? So how scalable our method? So we run experiments on like 250 nodes. This is the scale we run experiments with the edge that is the same number edge or 4 times the edge. So that's still finishing in reasonable time. So it's just in general deep learning based method. It's as scalable as like a regular flow based method on hundreds of variables. That should have no problem. If larger, it's just how long time you want to wait. And another advantage I want to say is for traditional causal inference method, if they select a treatment and control and target, they always need to re-estimate everything. But for our method, you kind of train the model, and after you train the model, you can specify your treatment effect and what you condition on, and then you just run forward passes where you just estimate the causal quantity without retraining the model. In some way, you can think it as amortized, that after training one model, you can answer arbitrary number of causal quantity estimation questions very fast.
I think you can read the questions there. I don't know if Cheng, if you find one that you want to answer. So there are plenty of questions. Maybe, I mean, I have actually one which is about the training of the method. Do you have to do any specific things for training? Because you have this, I mean, the distribution over the graph is binary. And then do you have any problems computing gradients there? Because you have to sample from a discrete distribution over your graphs. And then when you evaluate your objective function, it may not be differentiable with respect to the parameters of your.
So, I mean, we just use a standard gumball trick.
Okay, you use this thing to deal with the gradients. Okay, good.
So how sensitive the method to the prior chosen? I see you can have the question. So, I mean, prior you can have two type of prior. One is like kind of not very informative, just tells you how sparse it is. Another is can be more informative, like because for some case, let's say it's violate our assumption, it's not identifiable, you can have a little bit informed prior. So when it's informed prior, if the more confident it is, and the more proper, its performance better. And if you don't use that knowledge, then the performance can be very bad because the orientation is just random. And on the sparsity, just to be completely honest, I don't think we tested very much. Javier is in the audience, so maybe Javier can tell a little bit more. I don't think it's very sensitive among among this extremely sparse, a little bit sparse. But I cannot comment much more beyond that. But if Javier and Wenbo or Chao have more comments, maybe you can reply directly in the chat. Yes, so the functional causal model for causal inference, I mean, it depends. So, and also, yeah, so for example, some are very simple. For the node here, if it's just a linear, non-Gaussian, you have all the parameter, that is very simple. But if it is functional causal model, there is more of these methods are more hybrid. For example, nonlinear ICA methods, how they use for causal discovery in general is they do skeleton search. They use functional causal model like this, a lot of this self-supervised learning method for that, just to use some kind of independence or other assumptions to find the graph relationship. I don't think it's very easy to do causal inference for this type of framework. So very simple ones, linear ones, yes, for sure. But for some more hybrid or complicated ones, it's at least it's non-trivial.
Good. Yeah, I think in the interest of time, we are over the allocated time for the seminar. I think, yeah, if anyone has any more questions, they can write to Cheng or any of the other co-authors, and I'm sure they will be happy to address any of these. Thanks a lot, Cheng, for joining us today. And yeah, we are looking forward to more interactions in the future.
Yeah, thank you very much.
Thanks everyone for joining. Bye. Bye-bye.